In the previous video, whose link is in the description below, you used two while loops to determine how much time was required for the pendulum to swing completely through the laser beam. Specifically, at the conclusion of each while loop, you use the millis command to grab the time at each instant. Recall that millis returns a time in milliseconds. Furthermore, those times were stored as variables with the names initial time and final time, as shown here. Let's now calculate how much time was required for the pendulum to pass through the laser beam. Perhaps you already have coded this elapsed time yourself. Here is my solution. The elapsed time is just the change in time, so we calculate it by subtracting the initial time from the final time. Note, the elapsed time is also given in milliseconds. Run the code and change the sensor reading from light to dark and back to light again. This will give the amount of time that the imaginary pendulum blocked the beam and the sensor was in the dark. Next, let's calculate the average velocity of the pendulum. Physicists will often make rational assumptions to simplify a problem, and that is what we will do here. At the bottom of the pendulum's swing, its velocity is a maximum, while its acceleration is a minimum. If we assume this acceleration at the bottom is 0, the equation of motion becomes the displacement equals velocity times time. This can be rewritten as the average velocity is equal to the change in position divided by the change in time. To put it in more familiar terms, speed is distance divided by time. In our case, the time is the elapsed time we just calculated, which is the difference between the time the pendulum enters the beam and the time it exits the beam, as shown here. The distance traveled is simply the width of the object moving through the laser beam. Because our pendulum is a cylinder, the distance is simply the diameter of the pendulum, as shown. I fabricated these pendulums in our machine shop, and each diameter was measured to be precisely 25.41 millimeters. Because I may wish to measure the speed of another object in the future, I will store this value as a floating point global variable at the top of our sketch. Notice I am way up here on line 5. I'll name my variable diameter and set it to 25.41 millimeters as shown. Return now to the bottom of the loop function, being sure to put your cursor above the curly brace at the bottom of the loop function, as shown here. Now that the distance traveled and elapsed time have been coded in, try to write a line of code that will calculate the pendulum speed. Pause the video and give it a try yourself. Go on, you're not going to hurt anything. Okay, let's see how you did. Here is my solution. As explained in my comments, this is the speed of the pendulum and not its velocity. This is because we cannot determine the direction of travel with only one sensor. Also, convince yourself that if you divide a distance in millimeters by a time in milliseconds, the result is a speed in meters per second. In other words, there is no need to convert to SI units here. Making sure to enter code above the bottom curly brace of the loop function, let's show our results. That is, display the pendulum speed with units and a couple of separator strings so the user can easily view your awesome result. Note, in line 82, the command to print the speed has an extra parameter included. The "3" tells the microcontroller to display the value with 3 decimal places. Because we are measuring the diameter in millimeters and the time in milliseconds, we can display the speed in meters per second with this degree of precision. Run the code and move the sensor's slider to the brightest setting. You may also wish to clear the serial monitor. When you are ready to simulate a swinging pendulum, slide it to dark and quickly back to light. The speed should appear on the serial monitor as shown. If you toggle the slider quickly, the speed should be higher than if you toggle it slowly, as shown here. Again, the real-time clock of Tinkercad's slow online compiler will not be accurate. Nevertheless, we can still use it to show proof of concept. I encourage you to always check your microcontroller calculations with a handheld calculator. Quality control is an important aspect of physical computing. Before putting this code to bed, let's add a print statement to help the user know when it's okay to release the pendulum. Let's put it just before the first while loop near the top of the loop function, like so. Run it to see if this will help the user know what to do. We may now wish to comment out the print statements that display the raw sensor readings, since they are no longer useful to the human user. Do that now. Of course, if the sensor starts misbehaving or if the lighting conditions in the room change dramatically, you should uncomment them, as they can serve as a handy diagnostic tool. Note that if the lighting conditions do change, you may also need to alter the threshold value at the top of the code. Run the code one final time and see if you are happy with the results. Note that my connection with the Tinkercad server is a little laggy, so I'm having a difficult time getting the speed to be any greater than much more than 1 meter per second. Well, that's it as far as programming the microcontroller for our pendulum speed experiment. What comes next is loading all of this code into the Arduino IDE and uploading it to an actual microcontroller. We will also set up the real laser, light sensor, and pendulum in the laboratory. I will walk you through these processes in the next video. Thanks for watching.